Okay, welcome back. We're going to look at this is a continuation of calculus kind of whole review. Today, or this video, we're going to look at some SVA problems as well as some extreme values. So local max, local min, global max, global min. So here we go. So I'm going to give you recall. So this is going to be some SVA problems. And so I'm going to tell you that S at t, so the position at time t in meters from our, quote unquote home. Remember, we talked about what the idea of a home was. So S at t is going to be equal to 5t cubed minus 14t squared plus 5t and then minus 8. And so that's my position function. So recall that S represents position function. And I'm going to ask a few questions, and there are, kind of some standard questions, and one that will always come up. So I'm not going to make any mystery, no bones about it. If there were a midterm, if there were a final exam, and there was going to be an SVA question, one of the questions would have certainly been, where and when does this object come to a stop? So the first question is, where and when does this object come to a stop? Now, certainly, this would be the perfect opportunity for you to be pausing this and giving it a whirl. So go for it and come right on back. Okay, so here we go. So how do I know when something has come to a stop? Well, I know when something has come to a stop when, so we're going to qualify that. And we're going to say, well, that's when v at t would equal to 0. Because if my velocity is 0, clearly it means that I have come, at least momentarily, to a stop. So I know that v at t is s prime at t. So I'm going to find out what s prime at t is. Pretty simple derivative. It's going to be 15t squared minus 28 t plus 5. What am I doing here? Plus 5. Clean that back up a little bit. Plus 5. Here we go. So that's s prime at t, which is the same thing as v at t, right? Put that in there. And so if I want to know where I'm stopped, I want to know vt is equal to 0. So I'm going to say that 0 is equal to 15t squared minus 28t plus 5. And so can I common factor it? No, nothing can common factor out of that. So, some of you who are good with factoring by decomposition might try and decompose it. Some of you would be like, screw this and hop right into quadratic equation. Either way is good. I'm going to give it a whirl with decomposition. So I'm going to say AC is equal to 50 and 25, 75. And B is equal to negative 28. So that means I need two numbers that multiply to 75, and those same two numbers add to negative 28. That would mean then that it has to be, I guess, both negative numbers. So two negative numbers that multiply to 75. So, well, it's negative 25 and negative 3, I guess. So negative 25 and negative 3, right? Because negative 25 times negative 3 is positive 75. Add them up, it's going to be negative 20. So I'm going to decompose this. So we're going to have that 0 is equal to 15t squared minus 25t minus 3t plus 5. Do some greatest common factoring. So it's going to be 5t, which is going to leave me with 3t minus 5. Greatest common factor here is going to be negative 1. It's going to leave me with 3t minus 5. As always, if what's inside the brackets matches, I know that I'm on the right track. Greatest common factor those brackets out, so 3t minus 5 and 5t minus 1. There we go. It is factored. So I can find out when they stop. Well, I can set those equal to 0 and solve. So it's going to be stopped at t equals 5/3 and t equals 1/5. So this is the time that they stopped at. So that has answered the when has it stopped. To answer the where they have stopped, well, if I'm talking about where, I'm talking about a position. So I have to take those values and put them back into s at t. So I'll do that. And we're going to do s at t. So s at 5/3 is going to be equal to, and I'm going to grab my calculator that I've got sitting here. And just to speed things up a little bit, I'm going to enter that expression and then just use it to evaluate it. So we're going to say y equals, and I'm going to do 5x to the exponent 3 minus 14x squared plus 5x minus 8. And I'm going to ask it to ask me some values. I'd like you to ask me for the x values, go into the table. And the x value I want to evaluate is 5/3. So 5/3 is going to be equal to negative 15.41. So its position at 5/3 is negative 15.41. And then s at 1/5 is going to be equal to, grab my calculator again. So 1/5, go back down here, back over. So 1/5 to be negative 0.752. So here we go, negative 7.52. So negative 7.52. So the whens are 5/3 of a second and 1/5 of a second. The wheres are those two wheres respectively. So that's the first question. So where and when does this object come to a stop? So another question that we could ask, certainly we could ask questions such as, if we think about, different questions could come up. We could talk about when is it speeding up, right? Speeding up over what intervals? So not just make it like that. Speeding up over what intervals? Okay. So speeding up, you might think, oh, that means when it's got a positive acceleration. But we talked about that. To be speeding up, the velocity and the acceleration must be going in the same direction or have the same sign. So it means the sign of v at t and the sign of a at t need to be the same. So that means we're kind of going to need a sign chart that will allow us to figure this out. So I've got my v at t. Here it is right there. There's my v at t. I'm going to underline that with a different color so I could see it more easily. So there's my v at t. I also am going to have to obviously get what my a at t is. So I'm going to rewrite v at t is, I don't know what color that is, but I don't really like it. 15t squared minus 28t plus 5. And then I'm going to need a at t. And we have that a at t is going to be 30t minus 28. Now, I know when the zeros are for this. I've already found the zeros, right? So there's zeros for v at t. So the zeros are at t equals 1/5 of a second and at 5/3 of a second. So the zeros for this one down here, I don't even know if there's an E in that word or not. Let's pretend that there's not. You can make fun of me. Is going to be at t equals 28/30ths. So that would be 14/15ths of a second. So 14/15ths of a second is when that is. Now, we are going to need to know when they are positive and when they are negative. Okay, so you could use a sign chart to do that. You could totally break out a sign chart. You could be like, I'm going to do a sign chart for those and say, this is 1/5 and this is 5/3, and you could do your sign chart. Or you could say, heck, this is a quadratic, right? This is a quadratic that has a positive leading coefficient and it opens upwards. So this quadratic in the grand scheme has to look like this. It has to because it has a positive leading coefficient. That means that this is the first root is at 1/5, it's right there. The second root is at 5/3, it's here. That means that it is positive between 0 and 1/5, and it is positive after 5/3 and negative between those values. Okay. Similarly, you know a lot about this graph. This graph is it's a line. It's got a line. It's got a y-intercept down here at negative 28, and has a really steep positive slope that goes like, well, let's pretend it actually went through negative 28. Still not very good. There it is, closer to that. And so that it's positive from 0 to 14/15. So those are really relevant. So the way that I like to do this is I'm going to just kind of draw out a line here. And I'm going to say, all right, well, this is 0. And I'm going to add these other relevant values in. So 1/5 is, here's 1/5, 1/5. And then the next value that comes along is going to be 14/15. So out here, 14/15, 15ths, whatever. And then 5/3, 5/3. Okay, so those are relevant. So if we think, I should have done these in different colors. Whatever color this is, let's say that V at T is going to be, that's black. This color. Is that black? I think it's black, whatever. This color. Here it is. So blue or purple or violet or whatever it is, that color. So V at t, well, it's positive. It's up here until it gets to 1/5, and then it crosses down, and it stays negative from 1/5 all the way out to 5/3, and then from 5/3 and on, it is positive. Now, if you had a sign chart, you would have found that the result was positive, the result was negative, the result was positive, okay, which is what I've reflected here. And then A at t, let's get a different color. Let's choose that, but I don't even know, like green, yellow, puke, something like that. So this one, here it is. And I know that it is negative, right? It's negative up until that value. So here it is. It stays underneath, and then it hops above and goes this direction. So where is something speeding up? Something is speeding up where the signs are the same. Okay, so it is going to be speeding up. Let's choose this color for the where it is speeding up. It is going to be speeding up from 1/5 to 14/15, and it is going to be speeding up from, what number was that again? 5/3 on. Well, I don't need to put a cap on that because it keeps on going. So it's speeding up in that region. Okay, so speeding up over what intervals? It is going to be, and I know that we talked about the idea that some of them are going to be square brackets and round brackets. We're going to simplify our lives. I know that a lot of places don't chase that. So it's going to be speeding up over the intervals. That would be, I guess, from, let's just say, t a member of the reals, such that t is a member of, that would be from 1/5 to 14/15. 15ths, have a hard time with that one. Unioned with whatever the hell that is, 5/3 up to, well, forever. And there we go. So that's the region speeding up. Similarly, if I said where's it slowing down, it would be exactly where they are in opposite quadrants, not quadrants, signs, whatever. This would be it, and this would be it, right? Good to go. So speeding up over one intervals, there we go. So if I just want to know at an instant point, so if I said, hey, is it speeding up at the time of 3 seconds? You wouldn't have had to go to all of this work. You could have just put in V at 3 and A at 3, seen their signs. If the signs were the same, then they're speeding up. If the signs are opposite, they're slowing down. Okay, good to go. Speeding up over intervals, what else we could do? We could talk about returning home. Is it returning home? Returning home. And I'm not going to work this one out entirely. I just want to talk about it philosophically. If it's returning home, how do we know if it's returning home? Well, if we kind of think about, we should draw a line. Now, home is, very much in quotes. There is no home. But if it's returning to the 0 position, how do I know if I'm returning to the 0 position? Well, I need to know 2 things. I need to know the direction I'm going, but not only do I need to know the direction I'm going, I need to know where I am when that direction is happening. So if my position was negative, so if I'm over here in the negative region, but I'm headed positively, then I'm heading home. But if I'm in the negative region and I'm headed negatively, then I'm not heading home. I'm heading away from home. Similarly, if I'm in the positive region and I'm heading negatively, I'm heading home. And if I'm in the positive region and I'm heading positively, I'm heading away from home. Okay, so determining whether I'm returning from home or I'm departing from home, I'm going to have to look at 2 things. I'm going to have to check both position and velocity. Okay, so position and velocity are going to tell me whether I'm heading home or not. On we go. Next up, how about we think about, the classic ender to this is total distance covered. So total distance covered in the first n seconds. Doesn't really matter what it is, okay? And again, I'm not going to do all the work for this one. But what we have to consider is we have to consider where are we at, so we need our position at t equals 0, okay? There were a few people in the class that when I asked this question, they assumed we started at 0. In this case, we're not starting at 0. We started at -8, right? So position at t equals 0. Well, so S at 0 in this case was -8, right? And then we have to find the position of where we stopped. So stop 1, S at stop 2, however many stops are going to be. You're going to find those positions. And then you're going to need S at, this N value. So S at N. And there could be more. Like there's no limit to how many there's going to be here in theory. And then what we're going to do is we're going to do that graph. We're going to say, oh, we started over here at -8. And then stop position, we went up to, I don't know, whatever it was, 30. That's not what it was, but, it went over to 30. And then at stop 2, it turns out we were at -600, right? So we're like, oh, crap, UE, we're back here to -600. That's not a 6, -600. And then S at N is going to be, oh, it just goes back to 1, right? And so then we turn around and we go back to 1. And then what you're going to do is you're going to find out how long each of these segments are. So this segment goes from -8 to 30. So that segment was 38. This segment goes from 30 to -600. Well, that's 630. And that goes from -600 to 1. So that's 601. And then you'd add all those up, and that would be the total distance. Okay, so that's kind of SVA in a nutshell. Lovely. On we go. Extreme values. Again, I'm not going to fully work extreme values out. What I'm going to do is I'm going to hit the highlights again, the idea of what we'd have to test for extreme values. Okay, so if we think about extreme values, extremes, we're going to be broken down into two pieces. There are local max-mins, and then, of course, there are also global max-mins. Okay, so we got local max-mins, we got global max-mins. So local max-mins just means that you are bigger than anything else in your neighborhood. How big is that neighborhood? Doesn't really matter. As long as you're bigger than the value that's on your immediate left and you're bigger than the value that's on the immediate right, you're a local max. Or similarly, if you're smaller on either of the sides, then you are a local min. Okay. A global max means you are the highest point that exists over the interval that we are talking about. And same with a global min. Now, what all is eligible for these things? There aren't many things that are eligible. The only places that are eligible, and it's most easily seen from a graph. So I'll do a really quick basic graph. Speaking of basic, Jad, hope you're doing well. So here we go. So if we had this basic graph, and it went something like this. What a thing of beauty. Okay, there it is. So that's the interval we're working on. We're working from -15 to this looks clearly to be 17, right? Now, to be a local max or a min, it just means in your neighborhood you are bigger than the values near you. Okay, so this is bigger than the values near it. To the left it's smaller, to the right it's smaller. So this is considered to be obviously a local max. Okay, similarly, this guy down here would be a local min. Now, this spot right here kind of terminates right at 17. It is bigger than everything else in its neighborhood, so I'm going to identify that as a local max. Now, I don't know if I even talked about this in class, but in theory, there are some people that would argue that that is not a local max because we don't know about the other side. But it's not defined over there, so it is, to me, a local max. But certainly, if you're in post-secondary, it would be a good idea to clarify with your own TA what they decide that is going to be, because people kind of have their own little fiefdoms and they like it. Now, down here, clearly, this is also a local min. It's smaller or further down than anything else in its neighborhood. It's a local min. And global max and mins are the singular biggest and the singular smallest or most negative values that exist. So if we think about this one, the local or the global max is this fella right here. This is a global max. Not only is it a local max, it is also a global max. Okay. And this one down here would be the global min, because not mini, min. I'm just going to go there, min, because it is the smallest. Now, it's kind of funny. I talked about the idea that this might not be a local max. This is always considered considered a global min because it is the lowest value. But some people would say, oh, it's the global min, but it's not a local min, which is just nonsensical, because if you are the smallest value, the most negative value that exists globally, clearly that you must be the most minimum in your local neighborhood. Nevertheless, so global and local, global max, global min, we are only going to have one of each. A local min and a local max, there is no limit to how many of those there can be. Now, how do we identify these things? Well, they can come from two different places. They can either come from where f prime at x is equal to 0. That is one of the eligible candidates, so that's going to be a candidate. And why is that? Well, of course, it makes sense because it means that it has a slope of 0 at that spot. So it's got a slope of 0, it's got a slope of 0. So f prime at x is a candidate. Doesn't mean that it's going to be, right? There are cases where f prime at x can be equal to 0 that is neither a local min nor a local max. If we think about y equals x cubed, right? Y equals x cubed, goes like this. Well, let's pretend it goes like that. Right at this spot right here, doesn't look at from my diagram because it's garbage, but it is actually having a slope of 0. So if we did dy by dx on that thing is going to be 3x squared. At x equals 0, it's going to have a slope of 0. But it is neither a local min nor a local max. So that's why it is a candidate, right? So to check that, you can check a number of different things. You can check values on either side. You can simply use some of your knowledge of the function. Yeah, lots of different ways you can check that. Or you can check the concavity. Ooh, that's a good one. Alternatively, one set of candidates comes from where the slope is 0. The other set of candidates comes from the endpoints, right? So the endpoints are where the other candidates are going to be. So the slope is 0, or we have endpoints of the function. Endpoint being, where it is square bracket defined. If it is a round bracket definition of it, you cannot include the endpoints because it would be an open circle there. So imagine that it went like this. You couldn't say then maybe it came down to negative 16 is that's a 15. Negative 16 is the value that it went up to here. That would not be eligible if it's an open circle because it would be negative 15.9, negative 15.99, negative 15.99. There is no end to that game. So it will only work if the function, if the domain is defined with square brackets. Okay, it would sort of be a trick question if it was open. It's something that I would do for fun, but I'd feel bad about it later, maybe. Okay, so there you go. So we've talked about SVA and extreme values. Come back in a bit, and we're going to talk about some graphing.